multiple concepts in the computational study of correlated electron materials. So I will start my position as an assistant professor at Indiana University Bloomington in August, so in a few weeks. This is my email, faculty website and group website and so on. So to kind of advertise as junior faculty, I guess, should, our group is in the chemistry department, and, it is still open to people who, have a variety of backgrounds like physics, material science, and so on, as that's more of my background, for example. And, I have a variety of pedagogical talks also on YouTube on various topics, but here I'll focus on some particular ones, as you'll see. All right, so the goal of this talk is to kind of give some tools to understand some computational aspects of papers on correlated electron materials. So my PhD, for example, was more on the DFT side, and what I'm kind of interested in doing with this talk is to kind of explain some topics that I found were difficult in what I think is a simple way. Things like, self-energies, quasi-particles, and some topics that are often under debate, where I think it's important for people to kind of have a similar way of thinking about things and similar keywords, like how do we define the relevant D states in a correlated electron problem. And I'll also talk on some select topics from my work, including the electron crystal lattice coupling, Landau theories for superlattices as 1D model systems, and AI for materials discovery. So how do I think of correlated electron materials? So, mostly in my work, these are materials that have a transition metal. Of course, rare earth materials can also be correlated electron materials, but here I'll focus on transition metal materials. And the fact that you have transition metal ions leads to the possibility of open D shells, and as a result, specific ordered electron configurations, right? So here I'm showing, for example, a magnetic moment. If all your orbitals are filled or all your orbitals are empty, you can't have some sort of electron ordered configuration here. So partial filling is needed to have these ordered states, right? You don't have magnetic order with no electrons or when the shell is fully filled. Okay, you have a transition metal ion in a material, and what actually leads to all the interesting properties is that these open D shells interact with each other, right? So you have long range order, or possibly not order, maybe frustration, which comes out of an interplay of local and long range physics, right? So these atoms and their open D shells talk to each other, right? So this is an example. This is ferromagnetism. Localized states don't have to be orbitals, right? So increasingly, one of the things people are looking at are things like flat bands, for example, in Kagome materials, or bilayer graphene, right? So bilayer graphene, many people see it as similar, for example, to the one orbital bands in the cuprids. Right, so flat bands can be the result of particular types of orbital overlap. But generally, one way to think of these things is basically as emergent phenomena arising from these types of localized states. Right, so type 2 superconductors, for example, are seen as part of this category, while type 1 are usually not. Okay. And there's often some sort of interplay between different order parameters. So for example, there's this relatively new paper on, say, superconductivity and magnetism and their interplay, right? Okay, but key to superconductivity, we normally think of things like Mott physics and Mott insulators and so on. So what does Mott physics mean? Right, so suppose you have some sort of 1D chain of atoms, and you have one electron per one orbital, and you have one orbital per atom. So you have something like this, right? Okay. You have some interatomic hopping, let's call it T, and as a result, you'll have a band half filled here. So this tells you this should be a metal, but obviously if you move the atoms very, very far away, even though just a band theory would tell you this is a band half filled and this is a metal, of course, at some point you will have an insulator, right? And then the question is why? How do we model that? So, okay, one way to think of this is that you have things like piles distortions, right? So the atoms pair up in some way, and this actually leads to an opening of a band gap. So this is kind of the usual solid state class picture. Another way to think of this is that you have bonding and anti-bonding orbitals as a result of this pairing, and you have some sort of dimer pairs, for example. But it's often unclear what drives the transition, right? So is it, if you have something like this, is it electronically driven? Is it that the electrons want to pair up, or is it something structural? Anyway, so this is an important question, and I'll get back to this later, particularly how do we quantify electronic and lattice degrees of freedom and so on. But another option that you often get, for example, say DFT plus U calculations, if you're familiar, is you can open a gap with magnetism. So you don't need some structural distortion, right? You just have spin up, spin down, and again, you open a gap. So in this case, you also have a doubling of the unit cell, which leads to this band gap opening. And again, one way to think of this is you have an even number of electrons per unit cell. So you don't have to think of, odd number of electrons per unit cell. The question, though, is symmetry breaking really necessary to obtain an insulating state? So, and intuitively, the answer is obviously no, because if you have some atoms very far apart, you just don't have a metal, obvious, right? And one way to think of this is to think of the Coulomb repulsion U or Hubbard U between the electrons, right? So there is a cost for the electrons to hop from one atom to the other, especially as you pull the atoms apart, right? So large U over T, so T is the hopping, leads to a Mott insulator. Electrons are localized on the atoms. And this is where things like computational many-body methods appear and become important, right? This isn't a band picture anymore. This is some interplay of like bands and local electron physics. So a question then is, which mechanism do you actually have in a particular material, right? Do you have some Mott mechanism? Do you have magnetic order? Do you have lattice distortions? And the truth is that depending on the material, it's actually pretty hard to know, and it's usually some combination of multiple types of order parameter, Mott, magnetic order, lattice distortions, and so on. And I'll show a little bit some examples in my work. But what if you have a U that is non-zero, but your material isn't insulating? So this is where you start having things like correlated metals, right? So you have a band narrowing. So one way to kind of think about this is that the electron correlations make it harder for the electrons to hop. So you can think then of an effective hopping lower than the initial one. This is a very simplified picture. A slightly more complicated picture is that of quasi-particle bands, which comes from Fermi liquid theory. And you can kind of see this, for example, in DMFT, where, for example, when you do density functional theory calculations, right? So just band picture, you see this type of bands. When you add correlations, you see a band narrowing. Now, that's not the only thing you see, but this is one of the key things we look at and benchmark correlated electron methods, right? And this is true here. Compare the DMFT with IRPS spectra, and you see, again, this band narrowing. And of course, the other thing you see are Hubbard bands, which aren't really captured in this quasi-particle picture, as these are different types of excited states and multiplet states. Wait, so how do we think of this, right? So if you have strontium vanadate, You have one electron in the vanadium D shells, you have these quasi-particle states, and you also have these Hubbard bands. So these are very similar to what you get from band theory, but narrower, as I was showing. And these Hubbard bands basically correspond to, excitations that go from one multiplet state to the other, right? So from one electron to two electrons, you have some Coulomb repulsion U, for example. And there's a wide variety of types of methods to use this, right? So this is quite familiar, I'm sure, to many people here, for example, from Christian Halle's work. And you also have more simplified methods that can also reproduce the quasi-particle picture. For example, subsidiary bosons. So here advertising a little bit, one that I wrote. So one of the things that was very confusing to me when I started, doing DMFT calculations was the idea of self-energy. Like, how does this actually lead to these quasi-particle pictures? So here you can see, the DFT bands from this paper, as well as the DMFT results. Right, so you have the DFT band theory here, you have the quasi-particle bands, again, narrower. But you also see some are sharper, some are less sharp, and so on. And you also see further away some Hubbard bands. So the way you get from, I'll show a very simplified picture of how you get from, these particle states that we like to think we have in DFT to the how self-energies from DMFT give you this quasi-particle picture, right? So you have some band states from DFT, and you have from DMFT a self-energy. And, the self-energy is evaluated in DMFT, it's evaluated in GW, right? That's the main thing calculated by these methods. So one way to kind of think about it is if we have this wave function, right, we have the normal time-dependent evolution, e to it times the eigenvalue. Well, this self-energy does two things. One is it actually gives you a shift in the energy, right? So this leads to band narrowing, for example. And it also gives you a finite lifetime, right? So this now doesn't have an I in front of it. So this gives you the smearing. What does this mean? Well, once an electron is excited out of its state, the whole left will have, it will be replaced in finite time, right? That's like the Landau quasi-particle picture. And one of the things you'll see are things like this, right? Fourier transforms that go from this to something like this, which have a real part and an imaginary part. So this is a shift. Again, this should have an I in front, and this gives you a smearing, right? So this is what's plotted, basically. Right, so again, shift, and you have some smearing. And the cool visualizing tool to kind of play with quasi-particle states was built by Sophie Beck and Alex Hampel at CCQ, which is where I did my first postdoc with Andy Millis. Basically, what you can do here is add things like, what's a quasi-particle renormalization, and you will get some quasi-particle weights after you put in, say, some one-year function Hamiltonian, or even something you make up yourself. So it's kind of a cool tool to understand a little bit these things without complicated calculations. And again, you can compare the different things, right? So subsidiary bosons, like the version I have, doesn't give you the bandwidth renormalization, but you do get, it gives you bandwidth renormalization, but not the smearing finite lifetime approach. But you can get some of that even in this very simple quasi-particle picture, right? Okay, so again, there's no smearing if you use subsidiary bosons, not the type I worked on. Okay, so going back to this, this is how you read this type of plot, right? So the other question is, why are we only looking at one or two bands around the Fermi level in these calculations? I was showing this picture of this 1D chain of atoms, one electron per orbital per atom, and this is often the type of model that is filled, right? Again, you have these pilot distortions, all of these things, you can think of them in this very simple picture, even if the material is more complicated. So this is actually pretty common in physics models, right? Things like TJ models and so on. But one thing to kind of keep in mind that I think is interesting is, for example, this Peierls distortion for what I was showing is basically, if you just have one electron per orbital per atom, just leads to hydrogen molecules. So why do I bring this up? I'll show you in a little bit why it's important, right? So you have, say, 1s orbitals, you have these two hydrogen atoms together, you have some hopping T in between them, right? So set the on-site energies of these orbitals to 0. I have some intersite hopping, and then we have this matrix, and we have a bonding state, right? So that's the occupied state. That's what keeps the hydrogen atoms bonded. Has a negative eigenvalue, which is what stabilizes the hydrogen molecule. So you have this eigenstate that's 1, 1. Okay. You also have a positive eigenvalue, and this corresponds to antibonding orbitals, right? And this is empty. And the thing to keep in mind is, this is why you can't have, say, helium molecules, because you'd be filling this antibonding orbital and you'd destabilize the molecule. So general principle in many solids is antibonding orbitals destabilize materials. Right, this is kind of like a particle in a box analogy. You can think of this as, a ground state and an excited state. Right, so we now have this bonding and antibonding picture. Right, and one of the key reasons I'm going through this is because I want to explain what bonding and antibonding orbitals are and why they're important. Okay, so as I was showing you, helium is not stable. The antibonding would be filled, positive energy. And again, this is something important in materials design. If you have p and d orbitals, right, so going into more realistic materials, right, transition metal ions, you have some d state on, say, copper, and then you have some oxygen p states, right? You have a d orbital, p orbital. This is, again, super simplified, and you have some hopping t. And the difference here is that the d orbitals have higher energy to begin with than the p orbitals before you put the atoms together. So what do you end up with? Well, again, you end up with bonding orbitals and antibonding orbitals. So why does this matter? Well, because the energies aren't the same to begin with, you actually have a higher weight of the p orbitals in the bonding orbitals and a higher weight of the d orbitals in the antibonding orbitals. So why is this important? Well, it allows you to have different pictures, right? So you end up having, supposedly in many cases, you have some p orbitals lower in energy, antibonding higher in energy. And the interesting thing is that then you can pick your basis. So very often a lot of models are based on this kind of low energy picture of antibonding d orbitals, really, right? If you think of the atomic projections onto the atoms, then you have a more complicated picture, right? So where this part is a mix of d orbitals and p orbitals, while this part is a mix of mostly p and some d orbitals. And this ends up leading to pretty different pictures. So, you can build different models differently, right? So I'll show you a bunch of models that, use mostly this anti-bonding picture, and a lot of models do this. Other types of DMFT, for example, EDMFT uses all the orbitals, and then the model is more atomic-like if you want. So usually the terms people used when writing a DMFT paper will be something like, anti-bonding orbital, low energy model, D only model, or homolumo model. right? This is more of a chemistry term. So this is one way to build a picture, a physical picture, right? And in this antibonding picture, for example, why is this important? Well, if we shift, say, these states around, you will shift the amount of charge in these antibonding d orbitals. So this can seem like a little bit of a technical thing, but one of the interesting things is that in many materials, for example, the rare earth nickelates I'll discuss later, you can actually shift the antibonding orbitals, but the number of electrons in the atomic d orbitals actually stays the same. And that's because when you do that, you also shift the amount of covalence and bonding between the p and d orbitals, right? So this can be a more complicated picture. So it's worth keeping these things in mind, right? Because this is one of the things that happens at conferences. Someone presents something in a particular picture and someone says, well, but I understood it something different. And that something different is true in a different picture. Now, of course, the most complete picture is always the one that has the highest energy range, right? So that includes the most states. But it's worth keeping in mind, these differences in nomenclature also really correspond to differences in models. Okay. So this is kind of a representation of how you can have the same occupation in the d orbitals even as you shift the antibonding orbital along. Okay. Right, and you'll see pictures, different terms used, like ligand holes, for example, in this picture, as opposed to charge order, for example. Anyway, okay, and here I should keep in mind that I've used basically an LCAO approximation. Obviously, if you move atoms really close together, this idea that you have linear combinations of atomic orbitals stops being true, right? The helium s orbital is very different than a hydrogen molecule bonding orbital, right? So this is a simple image of this. And importantly, one of the questions is, why, depending on whether you've used Wannier functions or not, there's often this question of why do we use Wannier functions rather than just atomic orbitals? Well, like I was showing before, linear combination of atomic orbitals may or may not be appropriate, but Wannier functions are one way to build a complete basis set in solids. So here I'm showing an example in titanium chloride. And it's worth keeping in mind that the symmetry of your Wannier functions may depend quite strongly on the symmetry of your material. Okay, so again, basically Wannier functions can be used to build different types of models. So you can build Wannier functions, say, for this energy range, and you will get antibonding orbitals, or you can build Wannier functions for a bigger energy range, get more atomic-like orbitals. And these can be used as input to beyond DFT methods, things like dynamical mean field theory, subsidiary bosons, and so on. And many kind of analytical models of things like spin liquids and so on often do start from what is basically an approximation to some Wannier models, right? You have some hopping, you have some energy splittings, and so on. The choice of interaction parameters often depends on the basis. So if you have, for example, antibonding orbitals, right, these are bigger, right? So you have d orbitals and p orbitals together in an antibonding orbital, right? So then you'll have a lower Coulomb interaction. If you have a wider basis, the atomic local interaction will be larger, right? Things go like 1 over r squared, bigger orbitals mean lower u. So this is another thing to keep in mind when reading DMFT papers, DFT plus U papers, and so on, that the projections matter, and then the U you use may actually depend on those particular projections. So this all makes things often, quite complicated. Okay, so like I was showing, the local ionic environment plays a key role in correlated electron materials, right? So for example, if you have copper in a vacuum, its d orbitals will be degenerate from spherical symmetry. You put it in a cubic environment, if you think of antibonding orbitals alone, right? You have these d orbitals split this way, right? So you have 2 EGs and 3 T2Gs. And I'm not going into how the bonding p orbitals get split, right? If you distort the copper oxide bonds along the z direction, you will further break symmetry, right? So this is what people often call Jahn-Teller distortion, though Jahn-Teller distortion is a more general term actually related to symmetry breaking. But this is what people often call a Jahn-Teller distortion, right? The C over A coupled to this orbital order, right? But so you have 9 electrons in the d bands in this material, because you may have some rare earths here and so on, right? This isn't the whole picture. So then what you end up with is one electronically active orbital and everything else is filled. So many models for high TC superconductors really start from this, right? So you have a 2D lattice of copper atoms with one electronically active orbital. And of course, usually have some hole doping. It's not actually half filled. Okay. So many models are built this way, including models that are not, say, density functional theory or dynamical mean field theory driven, basically start from pictures like this. It's important to note that the charge transfer energy is still important. So, the charge transfer energy between the antibonding D and bonding P orbitals here. So for example, in this older paper from Gabi Cotier, for example, they found that the copper oxide apical distance is correlated to, the charge transfer energy, and this charge transfer energy is correlated to the TC. Now, of course, there are many other structural things that matter here, and this isn't, the strongest picture, but still you see this general trend, right? And the idea was basically that the charge transfer energy is correlated to the strength of the magnetic exchange. For a while, there was this topic of trying to design nickel-based superconductors, right? And how would you design nickel-based superconductors? Well, you try and have this picture again in one way or another. And, what do you want? Well, you want the d orbitals to be split in this way. You want to have around 9 electrons, maybe hole doped. And this was actually proposed over, 20 years ago. Now, of course, this actually worked, as most people know, right? So Harold Huang's group actually built neodymium nickel oxygen 2 by taking away the apical oxygens, right, with some chemical reduction. But for one of the interesting things about this, is I think in many ways this is maybe the first proposed superconductor from this type of principle. So one of the nice things is, predictive theories of, electron correlated electron materials do lead to new materials. And I should mention that before Harold Huang's work, there was a lot of work that was interesting. It didn't lead to superconductivity, including some work I was part of, where we were trying to design layered materials that would be superconducting, right? So some with nickel and some also with cobalt. And often the idea was along these lines, like you have some rare earth nickelate, right, which would look something like this. This would be its electronic configuration. And you put, say, something like lanthanum titanate next to it. So, and the idea is this titanium, its d orbitals are higher in energy than the nickel d orbitals, and you have a charge transfer across the interface coupled to, right, so you now have 9 electrons And this would couple to a distortion, right? Because you move one electron across the interface. This gives you a difference in charge on the ions, and then you pull this oxygen. And this would lead to this distortion. And this didn't lead to superconductivity, but the basic picture did work in terms of orbital order. And it led to pretty interesting physics. With cobalt, we worked in very similar directions. And it was kind of one of the most interesting things to me about this cobalt picture was actually that you had a 0.4 angstrom displacement of this oxygen. So quite huge. Okay, so now let me tell you in a bit more detail about one topic that's been dear to my heart, namely metal insulator transition materials. So 3 key topics in this direction. What are these metal insulator transition materials? Well, the first known one is actually magnetite, right? So this is ferromagnetic, as we all know, and it's metallic above 120 Kelvin and insulating below. So, if you take a picture of it, you'll see that it's shiny because at room temperature, it's metallic. And yeah, it's the first known metal insulator transition compound. And the idea with a metal insulator transition is basically that it's one of the most fundamental properties you can control, whether a material, whether a solid is a metal or an insulator. And separately, controlling the phase of a material also means you're controlling its properties, right? So if you have, for example, water, right, it'll have very different properties if it's solid or liquid or gas. But here we're not really thinking about properties like this. We're really thinking about the properties of the electrons with the lattice, with the crystal lattice almost the same. Another interesting part about phase transitions is that they're often heterogeneous, right? So this is pancake ice on Lake Michigan. And it's not just heterogeneous, it often has particular patterns, which can also be interesting and hopefully useful for technology. So how do these metal insulator transition materials behave? Well, at low temperature, they're often insulating. You raise their temperature, and at a particular TMIT, they have a transition, they become metallic. This is a very nice picture. Often this is what this looks like. For example, a thin film of neodymium nickelate. But the transition can also be smoother in some cases where it's obviously less useful technologically, right? You want to have 0 or 1. And there are many mechanisms that couple the electron and the lattice degrees of freedom throughout the transition. Another important thing is, besides temperature, you can force a transition with a strong electric field, right? If you want to build an electronic device, it wouldn't be very useful if the only way to force a transition would be with temperature. So if you're in the insulating regime in a material, if you apply a strong electric field, you can often drive it into a metallic phase. So you have something like this. And this push in this direction has really been, like, quite a bit of it has been to push towards neuron mimicking devices, right? So just like neurons, you apply a signal and the whole thing then conducts. So kind of this idea. And of course, an application would be things like machine learning and neural networks, right? So other applications can also be things like smart windows, for example, which just become metallic and shiny and prevent your room from heating up too much when it's very bright outside, for example. So, okay, what does that mean? Well, useful MIT materials, they should have a TMIT of over 300 Kelvin. We want them to be in the insulating regime so we can control them with a field at room temperature. And we want them to have a sharp transition. There should be a very clear difference between 0 and 1. And another thing that is also useful is to not have a very strong crystallographic lattice change throughout the transition. And that's for 2 reasons. One is it's faster to move electrons than ions, and two, you don't want the material to break, right? So VO2, bulk material can actually break as you push it through the transition. If you make a thin film, though, that often is kind of avoided. All right, so three topics I'll talk about briefly. One is the roles of the electrons and the crystal lattice in phase transitions. One is the heterogeneity of phase transitions. And one is how to use machine learning to hopefully discover new materials. And hopefully all these things can be useful in the future to design materials for a specific purpose. And I should mention, here I'm showing metal insulator transitions, but everything I'm showing is quite general to, correlated electron materials with phase change. Okay. So this part is mostly contained in these two papers, but really this is kind of a summary that will go through rare earth nickelates, calcium arsenate, and so on. And this is kind of a very old question in physics, in chemistry, in material science. You have a material or you have a molecule, and you have some crystallographic and electronic change. What is the role of the electrons in the crystal lattice through this transition? And can we have a switch without moving the ions? As I was showing, that may be quite useful for technological reasons. So a particularly useful example of materials are the rare earth nickelate perovskites, right? And they're a great model system as you can tune their transition temperatures with this rare earth, and they can be grown at very, very high quality. So in their high temperature state, they look something like this, right? So they're pseudocubic, you have a rare earth, nickel, and oxygen octahedra. And in an antibonding picture, you have one electron in the EG orbitals. You lower the temperature and you have a breathing distortion. And this breathing distortion gives you an empty, well, approximately empty nickel site and an approximately half-filled nickel site. So this is like what's called a site-selective Mott transition. Why? Because this is insulating, and at half-filling, this is a Mott insulator. This is a very approximative picture. It's more like 0.4 and 1.6, but not very far. Right, so we have a Q, which we use to describe the bond disproportionation. So how different are the nickel-oxygen bond octahedra in the big octahedron from the small octahedron. So this can be just a difference in average bond length. And to describe the electronic disproportionation, we use this difference in electron occupancy of the EG antibonding orbitals. And again, it's important to specify antibonding because if we were using an atomic-like picture, then there would actually be no difference in charge. Oh yeah. So the energy of the insulating state can be defined relative to that of the metallic state. So that's at Q of 0, delta N of 0, right? Everything is metallic, everything is homogeneous. So you have something like this. So this is a functional that characterizes the spring stiffness of the bonds, a coupling of the disproportionation of Q and delta N. One way to think of this is kind of like a difference, say, in atomic potential, right? So you have some atomic potential difference, and that's coupled to some occupancy difference, right? So you have some potential times charge, and that's an energy. And then you have an electronic disproportionation energy from this functional theory plus dynamical mean field theory. And this can be a little bit trickier to calculate. And it's a particularly novel aspect of this work is how do we do this within this particular picture. So, okay, we start with this energy functional. And we can impose stationarity. So the derivative with respect to Q will get rid of the electronic energy. and you end up with just this line. So this is a linear lattice response to electronic disproportionation, right? You move the electrons and the ions move around a bit. The more complicated part is the electronic part, which is not treated semi-classically. And that's because your delta n as a function of the distortion ends up quite a bit more complicated. Right. So you then have something like this. So in this paper, you have this line, which is the lattice response, which turns out to be the same for all these three rare earth nickelates. Right. This is your lattice response. It's a line. And the electronic part for small q, small delta n, you have a metallic region. And at some point, you have an insulating symmetry broken solution with a large delta n. And interestingly, in some materials like the lutetium nickelate, it looks like there may be an insulating state without any structural disproportionation, right? So Q of 0, and you have this very large delta n here. Okay, so these plots are kind of interesting, but then the question was how do you actually define the energy within this functional formalism with respect to Q and delta n? And this is what's in this paper. And the basic idea is as follows. You can also impose stationarity with respect to delta n in this functional. So then you end up with this very simple thing. And if you just assume the electronic energy is a polynomial, which in this case has to be even in delta n, right? It doesn't matter which way your breathing distortion goes. You are basically getting this as a result of DMFT calculations, right? So you can then do a fit and get the electronic energy by just integrating. And we can integrate because we only care about energy differences. We don't care about absolute energies, metallic versus insulating. So kind of a long-winded procedure, but it's actually pretty simple, right? You do some fits to the DMFT data. It fit remarkably well. And as a result, you actually get these energies. So you get three things. One, K is always positive. So maybe unsurprisingly, the lattice tends to not want to be disproportionated if you don't include these d orbitals. Interestingly, the electronic part also opposes disproportionation. So for all the materials we looked at, if you just have the electronic part, which you can also think of as the energy at fixed lattice, but moving the electrons, you always get any disproportionation leads to positive energy. But one of the interesting things, though, is like I was showing you for the lutetium nickelate, you do have metastable insulating states here, even at Q of 0. They're just not the ground state, right? So what really leads to the full symmetry broken state is this term here. So this term is actually always negative. And this tells you that the electron crystal structure coupling is really key to stabilizing the insulating state. Now, it's not like correlations don't matter. The electronic energy here, if I was to just do DFT, would be much more strongly positive and you would just not get an insulating state. So the DMFT calculation does lower these branches, but this is the main driver to stabilizing the insulating state. And one of the cool things is you can then get these energy landscapes as a function of Q and delta N. And you can see, well, for example, for neodymium nickelate, you have this metallic phase here, and then you have the two degenerate ground states here. And one of the nice things about this is that it's also computationally very inexpensive. And this also suggests, for example, and something people can probe through ultra-fast experiments, or maybe other experiments that you may be able to have electronic-only switching, for example, for lutetium nickelate. And this is kind of an important question experimentally as well. So for example, in the Ohm group, there was this paper on VO2 where they showed using some superlattices that it may be possible to have symmetry breaking in, say, only the Q and not the delta N or the reverse. Okay. So what can you actually say following this methodology? And I should mention this methodology can be applied, with DFT plus DMFT, but it can be DFT plus U. It can be a wide variety of methodologies. One of the things that's kind of interesting then is if you look at the rare earth nickelates, you see that you change the rare earth, you change the nickel-oxygen-nickel bond angle, right? So, and the more bent, the higher the MIT temperature. So what this methodology allows you to see is that there are two main effects. One, you bend the bond angles, obviously you have less nickel-oxygen-nickel hopping, and this favors a more insulating state, so this raises the temperature. The other interesting thing is that it also lowers the lattice stiffness. So as you go towards the lutetium nickelates, it's also the nickel-oxygen octahedra fight back less against the disproportionation, which is a new insight from this method. And again, it's kind of interesting that this is maybe coupled to the possibility of metastable solutions here. And one of the nice things about this method is we could use it on a variety of materials. So for example, say have control through layering. So you have neodymium nickelate, and you have superlattices of neodymium nickelate and a band insulator neodymium aluminate. And what we found from calculations is that the aluminum oxygen bonds resist the oxygen movement, right? So this increases the stiffness, effective stiffness of the nickel-oxygen octahedra. At the same time, the electrons can't hop to the neodymium aluminate, so this leads to confinement, which leads to a preference for an insulating state. So the lattice prefers a metallic phase, but the electronic part prefers an insulating phase. Anyway, experimentally, as well as from our calculations, it does look like overall the layered structures are going to be more insulating, and this is something that we've seen. Okay, so this can also be applied to materials like calcium ruthenate. Calcium ruthenate has a different MIT. You have a single ruthenium involved. You don't have pairs of atoms. The high temperature state looks something like this, 4/3 electrons per T2G. The EGs are somewhere out of the picture empty. And the low temperature state has one T2G filled and the other two half filled. And again, you have mod transition in these. So, we've applied this methodology, and you can read more in this paper to, rare earth nickelates, heterostructures with neodymium aluminate, calcium ruthenate, and one of the cool things is also calcium ruthenate grown on different with different epitaxial constraints. So the lattice alone will actually tell you which direction the substrate prefers an insulating or a metallic phase, even without doing new DMFT calculations. It matches surprisingly well. And the basic idea is, you just want to define a functional within a particular picture, obtain lattice stiffness, an electron lattice coupling, and an electronic energy. In the materials we looked at so far, the symmetry breaking is driven by the electron lattice coupling. And this is a very general model. It doesn't have to be MIT materials, right? Okay, second topic, and these ones will be quite a bit shorter, is that of heterogeneity. And here this is kind of a very interesting topic to me, particularly because of the approach, which was collaboration with experiments. So like I was showing you, transitions are heterogeneous, right? So if you look at neodymium nickelate undergoing a transition, you will see stripes of metallic and insulating phases. And you can also, and it's kind of hard to actually study these stripes, right? They're non-equilibrium, temperature matters, can be affected by things like light pulses, electric fields, and so on. And the question is also what leads to the size of these stripes. And these stripes, are of the order of, say, 100 unit cells. So it's kind of not really possible to do DMFT on that. So one approach is to look at layered structures of two different MIT materials as a 1D model. And the first paper in this series was this one, and all these papers are with Jean-Marc Giscon's group. And so it's a collaboration with University of Geneva, EPFL, ETH Zurich, and Technical University of Vienna, which started at a process session in Diable, not long before everything was shut down. So, collaborations that start from process sessions are often quite great. Anyway, so going back to this picture, this is where samarium nickelate is on the phase diagram. This is where neodymium nickelate is on the phase diagram. So you have samarium nickelate at around 350 to 400 Kelvin. It really depends. Here it's more like 350-ish because it's a thin film. And NNO in this thin film form, again, is at 100 rather than the temperature you see here. So when they looked at the resistivity versus the temperature, they found that up to 7 unit cells, they'd have a single transition. If you have 10, you have 2, right? This is a pretty long length scale. So, usually in this oxide heterostructure business, we really look at the interface and we see something at like 1 layer, 2 layers. This is 8 layers of each material, which led to this phase diagram. And again, a remarkable length scale for a single transition. There are questions, of course, like is there intermixing? And the answer is no. You can see the experiment is very clean. And then one question is, do these octahedral rotations that set the TMIT in the bulk material propagate? And the answer is no, whether you look at DFT calculations or you look at TEM. Though, it's worth mentioning in TEM, you can't really measure the octahedral rotations as much as you measure other structural modes associated with them, the displacement of the rare earth in particular. Okay, so one of the nice things is you can sometimes build theory that is very, very simple and still get surprisingly good results. So we can build a theory with some temperature dependence where the metallic phase is here and you have some n describing it. And we assume we integrate out the q somehow. Like I was showing you, it should be a bijection anyway, right? So for each q, you have a unique n. And then you also have an insulating energy, like the energy of the insulating state, right? And this is linear in T, and as T reaches TMIT, it's 0, right? So that's where you have the first order transition from one state to the other. So it looks something like this. Right, so you have 2 different materials, 2 different transition temperatures, and they're basically fully described by this slope. Okay, as well as the TMIT. So you put these materials together, right? One wants to be metallic, one wants to be insulating at a particular temperature. You also have an electronic and lattice mismatch. So you can build this full theory, but ultimately it doesn't really matter that much because it looks like the cost is very limited to the interface. Like I was saying, maybe 1 or 2 layers. So this leads to a constant phase boundary cost. So our theory then has this constant phase boundary cost and these slopes. And I'm cheating a little bit because for SNO, we actually assume a bit of nonlinearity, but you still have just 3 parameters. And the basic point is with 3 parameters fit to, 1 point here and 1 point here, you actually get the full behavior. And what does this Landau theory actually tell us? Well, it tells us that the transition in these superlattices is fully driven by a competition between a phase boundary cost between the metal insulating phase and the bulk free energy cost in each material. And one of the cool things was, this is very much confirmed by EELS measurements, where they basically looked at the order parameters as a function of number of layers, and you see that the part that is away from the bulk is really confined to the interface. And the reason to build this type of theory is to then, look at, for example, stripes in, a full material. So one way to extrapolate, like very back of the envelope, the length scales here are inversely proportional to the difference in temperature between the two materials. So if we think of a single material, which has a hysteresis loop of say like 10 Kelvin, instead of having 10 unit cell stripes, you end up having 100 unit cell stripes for this delta T of 10 Kelvin. So this ends up with the right ballpark. So this allows us to build theory using Landau theories extrapolated from a particular type of experiment. And I should mention this is an ongoing collaboration. We had quite a few more papers since. In this one, for example, we also studied the magnetism. And one of the interesting things is, the antiferromagnetic order in these materials in the bulk material only exists in the insulating state. In the superlattices, though, so you'd imagine, the length scales of the MIT have to dominate that of magnetism. That's not true. So the thing that turns out is that you actually have longer length scales of the magnetic degrees of freedom than the metal insulator transition. That's probably because the magnetic part is second order. And using this, we can build a variety of new theories as well. Another interesting thing was what happens if you add spacer layers between the two types of materials, between neodymium nickelate and samarium nickelate. So by spacer layer, I really just mean, lanthanum aluminate, just a boring insulator in the middle. Well, maybe it's not the most boring insulator, but it doesn't have this phase transition. And the result is actually that a single layer will fully decouple the materials. So you end up with a bulk behavior. And the reason you end up with a bulk behavior and why that's interesting and telling is that the lanthanum aluminate, it's also perovskite. It can also have a structural distortion. So that can propagate. But being an insulator, band insulator, it can't have the electronic order parameter. So what that kind of tells us is, well, it's really the electronic order parameter that leads to the propagation and coupling of the MIT in these materials. And this is kind of different than the bulk picture is showing it's the electron lattice coupling, right? And you can keep working on these things. So for example, if you have neodymium nickelate on strontium titanate, you can think of this as having different regions. So some non-bulk, some bulk-like, and you can basically build a theory that fully explains this very easily and have, a really great match. But either way, the basic point here is that in one of the interesting things is you have multiple types of theory that should in the future allow for simulations of real devices at different length scales. And the final topic I'll talk about a little bit is that of materials discovery using AI. So like I was showing you, we want new materials. We want them to have high changes in their resistivity, high transition temperatures, fast electronic switching. So basically, as you can see, the reason people tend to keep using VO2 for their devices is because it's here. It's above 300 and has a very sharp transition. As much as I like samarium nickelate and neodymium nickelate, right? Neodymium nickelate is under 300 and samarium nickelate isn't as sharp. And actually, the nickelates, the further you go in temperature, the less sharp the transition is. So yeah. You have a challenge then, you have a large material space. Like how do we even decide to look at the material and say it's an MIT or not? Like I was showing you, is quite complicated to even simulate a single material. And DFT is a T0 Kelvin theory. So how do you simulate temperature? Of course, there's ways in DMFT, but high throughput DMFT calculations may be tricky. Right. So this is the work I'll show here is really mostly in this work and in an upcoming work. And this is a collaboration from my time at Northwestern and James Rondinelli's group, with other groups at Northwestern specialized in machine learning, as well as Elsa Olivetti's group at MIT and Aubrey Toland, who's now at Georgia Tech. And I found it very important to work with groups that are really specialized in machine learning, as they often have a long history of figuring out what can go wrong or what can't, when are you overfitting. And the idea with this is to have an improved framework for materials discovery and understanding, right? So you have published work, you can search, you can find new materials, build databases of materials that have a particular property, and then hopefully machine learning analysis can actually help inform new models, not just new materials. And I'll share a little bit about how, and the basic idea is, the downside of the common approach of having, many studies on one material, like I showed you, have many on neodymium nickelate, is to overestimate the importance of what you can calculate with existing tools, right? So all you have is a hammer, everything looks like a nail, right? Everything is something I should build a basis for and do some DMFT calculations on. But the opposite approach in some ways what you find in machine learning, where you compare, say, all known compounds, hopefully identify some new features outside of the domain knowledge in that particular field, right? They're not fully out of nowhere, but for outside that particular field. And the first step was to build an MIT materials library. And there are some challenges. One, like I was showing you, DFT is a 0 Kelvin theory. So, last I checked, neodymium nickelate was listed as a metal in materials project. Maybe this was fixed, but it's definitely not, like I was showing you, is on MIT. But these are two useful databases nonetheless, and I'll show you how we make use of them. Then we can look at experimental databases. And, these are also useful, but they don't often have the classification we want. So, for example, nobody will label something as an MIT, an ICSD, or crystallographic open database. They'll maybe say semi-metal or something like this. Another difficulty, which is not unique to MIT materials, is that you have relatively few compounds. So for MIT materials that have a thermally driven transition, you have around 60 stoichiometrically distinct compounds with a very diverse set of mechanisms. So, you have breathing distortions, like I was showing you with the nickelates. You can have, the Jahn-Teller distortions, basically elongation of octahedra, like I was showing with the ruthenate. The vanadium dioxide has a Piles-like transition, right? So it's quite diverse. So the way we approach this in collaboration with Elsa and Aubrey was, they have a database of papers. We gave them some keywords, and then we did a sort of mixed NLP and human search and found new materials. So how this works, NLP found praseodymium, ruthenium, phosphorus. So this is a scuterodite. We confirmed it, by which I mean I read the paper and decided I believe it, and found this classification. And the thing to keep in mind is these scuterodites are actually somewhat well studied in the thermoelectrics community. They're just not really well studied in the correlated electron community. And we also discovered a similar compound, this one. And the key reason why we needed NLP and particular keywords is because, if I simply use Google Scholar, Google Scholar will kind of know my interests and it will keep giving me neodymium nickelate and vanadium dioxide. This NLP search has a little bit less of this bias of what will I click on, right? So it gave maybe a more neutral result. Importantly, it also gave many results that are not MIT's, but that's something I as a person can then discern, right? When you use Google, you don't click on everything, right? You pick the important result. Google wouldn't be terribly useful if you only had the first result all the time, right? Okay, so as a result, we have a database of, binary, ternary, quaternary materials. So binary, is like nickel oxide, like 2 atoms. Ternary is 3, quaternary 4. And these are classified based on high quality experimental data. So again, I read the papers. We have a total of 343 materials, and the basic point is 68 are MITs, and the rest are related to them in some way, stoichiometrically or crystallographically, and so on. So Kyle Miller, who's a grad student in the Rondinelli group, was playing with some data visualization tools, and we are very grateful for the great job he did building this database, where you can now look and see the different compounds as well as the features we use to describe them. And I'll show you how we pick these features. So we download the CIF files, experimental ones, and we pick the metallic ones, right? We don't want to have, particularly for training purposes, you don't want to have the same material twice. And we pick the metallic structure. The reason we pick the metallic structure is because if you already know the insulating distorted one with, the 0.1 angstrom displacements, it has an MIT. So the more important thing is, you've already characterized it, is to kind of know better the less well-characterized structure for high throughput discovery, or, someone can upload a CIF file. And we featureize these structures directly using Python scripts, no DFT. Again, DFT comes in at a later level. So we then used a variety of features from domain science. Some compositional features from MagPy, some structural features, including some hand-built features that Peiwen, who is an undergraduate student in the group, built, namely the Hubbard U and charge transfer energies, as well as a global instability index, which I think is now actually standard in materials project. And what this tells you is how different are the bonds from the ideal. Ideal is a sort of average over many materials. So obviously, we're not doing CRPA on the materials. It's not a very calculated, very involved calculation, right? We get unscreened Hubbard U's, and that comes from an ionization potential, an affinity, and an electrostatic response, right? So you have a transition metal, what's the energy to move an electron from here to here with no screening and everything atomic energies. The models used for classification is XGBoost. So XGBoost is a tree-based model. It's not a neural network. And the reason for that is tree-based models actually work when you have relatively few compounds. In order to avoid overfitting, we only picked 10 features. Some are things like the Hubbard U I was showing you, and some are automatically down-selected by the code using F1 scores. And it becomes quite interesting, right? So you can look at, for example, some well-known features like the metal-metal distance and Hubbard U. So metal-metal distance is between the transition metals. And one of the things it's kind of a proxy for is bandwidths. While the Hubbard U is, unscreened. And I'll show you also why this is 60, because that's wrong, and it's wrong for a particular reason. Okay, so another feature, well, actually, I should explain that the reason why this is 60 is actually because our code, the way it featureizes everything is assuming everything is ionic. And here you actually have quite a few covalent bonds, and ruthenium is actually D5. In our model, ruthenium ends up D0. So that is one of the difficult things with machine learning, is once you go outside of, say, a particular type of material, how do you featureize outside that in a way that makes some sense, right? Ruthenium here at D0, of course, would have 60 V or something Hubbard U, but it's actually D5. Okay. Another interesting feature was the average deviation of the covalent radius. And, this is a handful to say, but all it tells you is how different are the atoms in size in a particular material. If you have a material that's just iron, for example, that's 0. All the atoms are the same size. But if you have different types of atoms, you have some deviation, right? So this is the average deviation of the covalent radius. And why is that interesting? Going back to my favorite materials family, the rare earth nickelates, you can plot this ADCR as a function of, well, TMIT as a function of ADCR, and you get more or less the plot you saw before. And, again, this is the rare earth family, and you change the rare earth, right? And the reason is this ADCR is linearly correlated with the well-known tolerance factor, which people use to approximate, the mismatch between atom size, which leads to, octahedral rotations. Okay, so the reason this is interesting is this ADCR has no information about the geometry of the material. So this leads to a question of, can we use this ADCR as some sort of generalized tolerance factor? There are other features that are also interesting, and again, they come with some caveats. But this Ewald energy per atom is a measure of the ionicity of the material, right? So electrostatic energy of the ions. So if you look, for example, at the vanadium oxides, VO is metallic as it's quite covalent. The MIT vanadium oxides are in the middle. And then you have the insulating vanadium oxide here. Okay, so Baywen, who was an undergrad, I commented in the group at Northwestern. He won a Hilliard Award for this work, and he's now doing a master's at Stanford. And he also built our classifier tool into binders, so you can just use that directly. So the way this works is you go to the Rondinelli group website, and you upload the structure, right? And it will take a while to load. The first time it will take a while longer because it's basically installing in your browser. And then, you can look at the different features. You can also look at the folders and so on. Nothing gets saved, so you can't edit anything in a way that's not recoverable. You can add a new structure, a new zip file. It can be featureized. If it's confused about the ionizations and so on, it may ask you for some help, right? And then you can get a binary prediction. Is this metal or not? Is this insulating or not? Is this an MIT or not? The reason is binary classifiers tend to be more accurate than ternary classifier if you have so few materials. And then you can also see where the new material you added is, right? The orange dot, well, the red dot here compared to the materials already in the database. You can also upload the folder, and there's a high throughput version of this there as well, like if you scroll down. Anyway, so you get a classification within seconds, and this is linked to in our paper. So, here the basic point was we use machine learning tools at all levels of quantum materials discovery. The first part was to build this database. Then we built this model that we can use for filtration of multiple materials. And then we use this model on the materials project. And then on these models, we selected a few materials and we performed some detailed calculations. So we got a wide variety of structures, different transition mechanisms. And one of the interesting things, again, is from NLP, we got different types of possible synthesis methods. Okay. So, in this way, machine learning can help accelerate discovery as well as synthesis of new materials. So yeah, these are the key results, and there will be a new paper as well on these compounds. And, one of the things here is like where to even get started with things like machine learning. And, to me, the most useful part is actually Kaggle. So Kaggle, is an open source website. It's all like Jupyter notebooks. And it gives you a variety of examples, and it also tells you a lot of things about how to visualize data, how to not trick yourself. And then it also has real life competitions that, I can't say I've really played with a lot, but they're quite good. The only caveat with competitions is that A, they take a lot of time, and B, after a certain point, you may be overfitting the model to whatever gives the best result for that particular contest, right? So you want to avoid that. And another thing that's quite useful, is the API for materials project. So the filtering we did of these materials is actually using materials project, downloading stuff into our classifier, featurizing and having predictions. So materials project is actually quite user friendly. So yeah, I showed you a few things, on how to read correlated electron papers if you're not used to them, a few things on the crystal lattice and electron coupling, heterogeneity of phase transitions, and materials discovery. Hopefully, these three topics can be used in the future to design materials for a specific purpose. And, like I mentioned, I am starting my group now. So, yeah, this is the topic I work on, and I have quite a few more pedagogical videos on my YouTube. So thank you.
Thank you, Alex. Very nice talk.
Yeah, thank you so much. That was great.
A lot of new results.